Welcome to this explainer. Today we're looking at how a tiny, seemingly insignificant anomaly involving sparks on a piece of metal ended up completely dismantling classical physics and, well, giving birth to quantum mechanics. I'm honestly so excited to guide you through this one because it's a perfect example of how looking really closely at the absolute smallest mysteries can unlock the secrets of the entire universe.
Okay, let's dive right into this by asking a pretty bizarre question. How does an 1887 experiment involving simple zinc plates connect to moon dust mysteriously floating in the vacuum of outer space? It honestly sounds like the setup to a sci-fi movie, right? But the answer is a very real, invisible quantum mechanism that is literally happening all around you right now.
To solve this mystery, here's our roadmap for the explainer. We'll be hitting a glitch in classical physics, Einstein's radical photon hypothesis, the quantum prison break, the birth of quantum mechanics, modern tech and attoseconds, and finally, spacecraft and levitating dust. Let's get to it. Section 1. A glitch in classical physics. The mystery of the glowing plates. Let's start our detective story back in the late 1800s. At this point, physics seemed to have almost everything figured out. But then, a few curious scientists noticed a glitch. In 1887, Heinrich Hertz discovered that shining ultraviolet light on a zinc plate produced visible sparks. A year later, Wilhelm Hallwachs showed the same light caused uncharged metal bodies to suddenly become positively charged. Nobody actually knew what was being knocked out of the metal until 1899, when J.J. Thomson identified these invisible escaping particles as negatively charged electrons. We now call this the photoelectric effect. And this is where scientists ran into a massive problem. According to classical physics, light was a continuous wave. So if you shined a really bright, intense light on a piece of metal, that energy should gradually heat up the electrons until they eventually just boil off and escape. But that is not what the experiment showed. Instead, electrons were ejected instantly, and their energy depended entirely on the color or frequency of the light, completely ignoring how bright or dim it was. A dim ultraviolet light worked perfectly, but a blindingly bright red light did absolutely nothing. Classical physics was just utterly broken by this. Section 2. Einstein's radical photon hypothesis, rewriting the rules of light. Enter Albert Einstein in 1905. To solve this impossible puzzle, he proposed a radical, almost unthinkable idea that challenged literally everything scientists thought they knew about light. Instead of viewing light as a continuous flowing wave, like a constant stream of water from a hose, Einstein argued we should picture it as discrete, individual packets of energy. Think of it less like a river and more like a flock of flying birds. He called these packets light quanta, which we now know as photons. And he used a beautifully simple equation, E equals hf. The energy of a photon is directly proportional to its frequency. So the crucial point here is that a single electron in the metal will absorb exactly one of these birds, or photons. If that photon has a high enough frequency, it instantly gives the electron all the energy it needs to break free. No gradual heating required at all. Section 3. The quantum prison break. Understanding the math through analogy. We can easily explain Einstein's brilliant math using a simple prison break analogy. Imagine the electron is a prisoner locked strictly inside the solid metal. First, we have to define the work function, represented by a W, or sometimes the Greek letter phi. Think of this as the bribe money required to pay off the prison guards. Every type of metal has a completely different work function. It's the absolute minimum energy cost required to tear an electron away from the surface. Now, because photon energy depends on frequency, there is a threshold frequency. This is the exact color of light that brings just enough cash to match the work function. It's the minimum energy required to even attempt the escape. If the incoming light is below this frequency, well, the photon just doesn't have enough bribe money, and the electron is permanently stuck in prison, no matter how incredibly intensely you shine that light. So watch how this all builds together. Step 1, the photon smuggles the money in. Step 2, the electron pays the work function bribe. Step 3, any cash left over becomes the electron's getaway money. That's its kinetic energy. So the kinetic energy of the escaping electron is exactly the incoming photon energy minus the work function cost. This beautifully and cleanly explains why higher frequency light results in faster, more energetic electrons. Section 4. Birth of quantum mechanics. The ripple effects of 1905. Einstein's explanation was a massive triumph. It proved that light actually acts as a particle a concept that completely overthrew classical physics and really opened the floodgates for a brand new era of science. Notice the rapid momentum here in the early 20th century. We go from Max Planck proposing energy quanta as just a mere mathematical trick in 1900 to Einstein proving they represent physical reality in 1905. And this directly inspired Niels Bohr's quantized model of the atom in 1911, which then paved the way for Arthur Compton's groundbreaking experiments in 1923, fully establishing wave-particle duality.
It's also super vital to contrast how photons interact with matter depending on the situation. In the photoelectric effect we've been talking about, the photon is entirely absorbed. It vanishes, giving 100% of its energy to the electron. Now, in pair production, a high-energy photon literally transforms into an electron and a positron. But in Compton scattering, the photon acts way more like a cue ball on a billiard table. It collides with an electron, transfers only a portion of its energy, and just bounces off at a different angle. All of these phenomena definitively prove light behaves as a particle, just under slightly different rules of engagement.
Section 5. Modern Tech in Attoseconds, the invisible engine of our world. So why does all this century-old physics matter to you today? Because this exact quantum effect is the invisible engine powering the modern tools you rely on. Every time you use a digital camera, you're relying on image sensors that perfectly convert incoming photons into electrical signals. In scientific labs, photomultipliers use this effect to detect incredibly faint levels of light. And night vision goggles, they rely on thin films of materials like gallium arsenide, which have a very low work function. When faint photons hit that film, electrons are ejected, accelerated, and multiplied to create a visible image in total darkness. And what's truly mind-blowing is the sheer speed at which this happens. Modern spectroscopy reveals that this emission isn't some slow, gradual process. Electrons are ejected in attoseconds. That is 10 to the negative 18th seconds. We're talking a billionth of a second. The transfer of quantum energy is, for all practical purposes, completely instantaneous. Section 6. Spacecraft and levitating dust. The photoelectric effect on a cosmic scale. Finally, let's zoom out from the microscopic, everyday tech and look at how this impacts exploration on a cosmic scale. Because the photoelectric effect doesn't just happen inside your camera, it happens out in the harsh vacuum of space. Out in orbit, the sun's relentless, unfiltered ultraviolet rays constantly bombard the metal hulls of satellites and spacecraft. Just like Hertz's zinc plates, that UV light violently ejects electrons right off the ship. This leaves the spacecraft with a dangerous, massive positive static charge buildup. It creates a severe imbalance with the surrounding space plasma that can suddenly discharge and completely fry delicate electronics. It's a huge hurdle that aerospace engineers have to actively manage. And that brings us perfectly back to our hook at the very beginning of the explainer. This exact same photoelectric effect is happening right now on the moon. Unfiltered solar UV light hits the lunar surface, knocking electrons right off the moon dust. Those dust particles suddenly become positively charged, and because like charges repel, the dust literally pushes away from itself. It electrostatically levitates, creating these bizarre, glowing fountains of dust just hovering above the lunar surface. So as we wrap up this explainer, I want to leave you with a provocative thought. If the seemingly continuous light hitting your skin right now is actually a discrete swarm of quantum particles, capable of kicking electrons out of solid metal and levitating dust on the moon, what other invisible quantum mysteries are hiding in plain sight, just waiting to be discovered? Keep questioning, keep learning, and I'll catch you in the next explainer.